COVID-19 is set apart from all other strains of flu for the simple reason that people die from it at higher rates than from other varieties. It follows that understanding the actuarial details and consequences of this virus is central to understanding its potential impact on the U.S. population in particular and on the world population in general. Here I ask three questions. The first is related to case fatality rate of COVID-19. The second concerns the age-specific mortality of this virus. And the third to its demographic consequences were no health-related intervention policies implemented or a vaccine available. So the first question is, how does COVID-19 case fatality rate vary across countries? We define case fatality rate as the death rate per infected individual. It's computed as the number of deaths due to disease divided by the number diagnosed with a disease, which is to say the number of cases. We see here COVID-19 deaths relative to the number of cases in 185 countries. I got this data from the Washington Post. They have it listed every day, updated every day by country and number of cases and number of deaths. So you see here on the bottom that the x-axis you have the number of cases. This is in a log 10 scale, so every tick mark is an order of magnitude change, the same scale for the y-axis for the number of deaths. The first thing that jumps out of this graph is a huge variation within number of cases for the deaths. And so, for example, you see only 10 deaths for cases ranging from 100 cases to 10,000 cases. Another way to look at this would be for 10,000 cases, it ranges from 10 deaths in some countries to just short of 1,000 cases in other countries. And so you have here some of the points. You have U.S., which is the highest number of cases and deaths, Italy, China right there. You can see these countries here would be Mexico and Singapore. So you see Singapore has 10 deaths for 10,000 cases. Mexico has about 800 deaths for 10,000 cases. Huge variation. Now, if we look at the distribution, frequency distribution of these case fatality rates across these countries, so you see at the bottom would be case fatality rate, and the y-axis the number of countries. So for example, we have Germany and Portugal, fairly low case fatality rate of about 3%, US, China, and Austria about 5%, Mexico and Indonesia 8%, Italy, Netherlands, and France 11%, and Belgium and Nicaragua 15%. If we take the mean of all those percentages by country, it's about 3%, whereas if you look at worldwide and you do all the deaths worldwide and all the cases worldwide, the case fatality rate is about 7%. A second question is, how does the level of age-specific mortality change when COVID-19 is incorporated as a competing risk? We first define age-specific mortality as a fraction of individuals alive at age X that die before age X plus 1. Here is an age-specific mortality for U.S. females in 2017. This is, I consider, the baseline. So we have age on the x-axis and mortality on the y-axis. Here we have 1 out of 2,300 20-year-olds die before 21, 1 out of 700 40-year-olds, 1 out of 150 60-year-olds, 1 out of 25 80-year-olds, and 1 out of 2 are a flip of the coin for 100-year-olds. I used Imperial College Response Team report with data on the case fatality rate. You have age group here on the left column and the case fatality rate on the on the right column. And here would be this baseline mortality as we saw before, and I created an exponential mortality curve that includes every age from 0 to 100, informed by the data from the Imperial College group. So there you have in red this COVID-19, and then if you combine them, you have a baseline plus the COVID-19 mortality curve. And so you can see here that the 65-year-old now has a mortality risk of an 80-year-old. You can say more generally that with no COVID-19 intervention policies or vaccine, the entire population at all ages is subject to mortality risks equivalent to persons 15 years older. So in other words, 80 is the new 65. A third question is what would be the demographic consequences of 100% of the U.S. population becoming infected with COVID-19 and thus subject to the new mortality schedule. We have here the 2020 U.S. age pyramid, where you have number on the x-axis for males and females respectively, and age class on the y-axis. So that with the U.S. pyramid with the entire population subject to unmitigated COVID-19, you see the band here, this is excess COVID-19 mortality. It totals 5.7 million deaths. We have here estimated age-sex distribution of COVID-19 deaths in the U.S. with non-intervention. So the band you saw on the last age pyramid is now replotted, and so this is the distribution of deaths. You see here again, it's a number in thousands. It's a different scale in age class on the y-axis. There's a total of 5.7 million deaths, as we noted earlier. There's 74 years was the mean age of death for males and females. They differ slightly, but it's fairly close. And there's 70 million person years lost because each of those individuals who died had a remaining life expectancy of about 12 years, as it turns out. The transient demographic consequences of COVID-19 non-intervention are the following. Period male life expectancy, this is cross-sectional life expectancy, and so it's transient. It's currently 76.2 years. It would be reduced to 66.1. Female life expectancy is currently 81.4. It would be reduced to 68.5. Average age in the U.S. is currently 39.3. It would lose a half a year to 38.7. And the percent of the U.S. population over 65 would be 17.1%. Currently, it would be reduced by over a percent to 16%. The last question is, what will age-specific mortality look like in the post-pandemic world? This is in the category of disaster demography, where you'd have either or both demographic selection and or scarring. And so again, here's our baseline age-specific mortality along with the disaster. The question is, would that red curve return to the baseline? There's a couple, these two different possibilities are that you could have scarring. So for example, you'd have increased mortality due to sustained organ damage, which is one of the long-term consequences of COVID-19 survivors. The other possibility is that where you have selection, and that is reduced mortality due to the removal of the frail, so that those that survived COVID-19 are the more robust, and the ones that were more frail were selected out. There's examples in the literature for both the scarring and the selection. I'll illustrate the importance of these studies, noting the challenges of estimating fatality rate. You have case fatality rate, which are, as you recall, deaths per detected case. But there's also another metric called infection fatality rate, which is a deaths per detected and undetected case. So you see the iceberg metaphor concept in the lower right. Everything above the surface there would be the detected cases. And so with the those detected cases, you'd have a 10% estimate of the fatality rate. On the other hand, if you could detect what's heretofore been undetected, then you would have a fatality rate of 0.01. We're talking about a 10-fold change. Fatality rate is central to the concept of herd immunity computations. Early in a pandemic, one infection generates several others, since virtually no one is immune. Because survivors of the infection become at least partly immune, the proportionality of immune persons in the population increases later, so that eventually infected persons are only infecting one person, even though they have the potential to infect more. Using 3 as the number of new infections per infected person, known as the reproductive rate R. This means that if 2 of 3 persons in a population are immune, then infected persons are infecting only 1 new person out of the 3 possible, and herd immunity is attained. That is, the rate of spread is reduced to 0. Herd immunity in the U.S. will be achieved when 220 million people are immune, or 2/3 of the total population of 330 million. If the fatality rate is 1 death per 100 persons, or 1%, then 50,000 deaths implies that there are 5 million persons immune. But if it is determined that fatality rate is 1 death per 1,000 persons, or 0.1%, then there would be 50 million persons immune, or nearly a quarter of the population needed for herd immunity. I will close by noting that, in sum, understanding the true COVID-19 fatality rate is of great importance because it is needed to estimate the number of persons who will die under different mitigation scenarios and, along with death statistics, how close we are to achieving herd immunity. Thank you for watching.